Okay, so where we left off, I was kind of threatening with Ohm's law. I was telling you guys, our series circuit, our parallel circuits, our combination circuits are kind of looming a little bit. They don't do a lot as far on the test as far as calculations for series and parallel directly. The calculations rather all lie in the combination circuit problem, or a couple combination circuit problems. But obviously indirectly we need to use series and parallel circuits to solve this combination circuit. And I'm going to show you what I think is hopefully a nice easy way, kind of a direct way to maybe tackle that combination circuit. But we first need to be reminded of our series circuit rules and our parallel circuit rules, right? Series circuit, our voltage is additive. Our amperage is equal all throughout the circuit. Our resistance is additive. Our power is additive. For the parallel circuit, our voltage is now going to be equal, whereas our amperage is additive. So these two flip-flop between parallel and series, don't they? For resistance, we have this big, long, crazy formula. As usual, we're going to avoid that thing like the plague, and here, again, is no exception. We're going to avoid that pretty swiftly. And then one thing that does not change between series and parallel is that our power formula is going to remain the same. Its good power is going to be additive as well. And this is something I just sort of discovered pretty recently, a little trick we can do using power. So I haven't taught it to you guys prior to this because I just figured it out myself a couple days ago. So we're all learning here together. But anyway, so a combination circuit. This picture right here I copied directly from the test. Now the values I'm giving you are different. Obviously I'm not going to just give you the test question. But this is the type of type of combination circuit question that's going to be on the test. I think there's 2 or 3 different scenarios, and they all use this exact same, what I'll call the circuit shape. And I call this sort of a square circuit. Reason being, we have 2 loads, or 2 rungs of the ladder, 1, 2, and each rung of the ladder consists of 2 loads, 1 here, 1 here, 1 here, 1 here. So it's kind of a 2 by 2, if you want to think of it that way. These circuits are kind of squared off. So the first thing we got to do is sort of successfully identify this as a combination circuit. And we've kind of already done that because I told you. But the reason it is, if we look at R1 and R2, R1 and R2 are connected in series with one another. R3 and R4 are connected in series with one another. But now if we sort of mentally combine R1 and R2 and treat them as one load or one element, and then do the same with R3 and R4, this R1-2 section is in parallel with R3 and 4. So we have some elements or some components that are in series. We have some that are in parallel. Because of that, it's a combination circuit. What do you know? So how do we solve this thing, right? And I'm going to give you some shortcuts. This is going to be as close to a step-by-step scenario as I can give you. I can't give you step-by-step because the values that you start with are always different. But this is as close to that as I can do. Again, keeping in mind all of your circuits on the test are these square type circuits, 2 by 2, and they all use elements that are all equally rated, right? So that's the first thing we got to know. All these elements are equally rated. In this case, let's just throw out there they are rated 2,000 watts at 250 volts, okay? So right off the bat, I mean, you already see I already have this grid here. I'm a big component of this grid, or I'm a big proponent of this grid system that I like to use. Draw the grid, I'm telling you, even if it's just one question, draw the grid, start solving, and I mean, treat this like a bingo game, right? So speaking of bingo, first, right off the bat, we always have a free space. They have to tell us what our source voltage is. That source voltage is going to be total voltage in all these cases. Our source voltage here is 480 volts. They have to tell us that. So right off the bat, let's fill that thing in. Now, where these things get really tricky is we can't really use any of these rules directly, the series rules or parallel rules, to fill in these columns. Reason being, these columns represent a combination circuit. They're not purely series or parallel, so we can't use those rules yet, right? So there's really only one more thing we can do at this point based on what we know right now. And that's going to be, we could find the fixed resistances. See, I told you that term was going to haunt you for the rest of your year 1 term here. We can find the fixed resistances of the individual elements, R1, 2, 3, and 4. We can do that because we have nameplate wattage, we have nameplate voltage. We can use our good friend Ohm's law right up here to do that. Before we do that, however, I'm going to give you kind of a cheater way here, right? This only works in these square 2x2 type circuits that have all equally rated elements. This is the only time this is going to work. I know that voltage in a parallel circuit is going to be equal everywhere. So the voltage applied to this rung of the ladder is going to be equal to the voltage applied to this rung of the ladder. And if I use some common sense logic, I can tell that since this is connected straight back to voltage, this is connected straight back to voltage, that's going to see full voltage. It's going to get 480. So this rung of the ladder is going to have 480 applied to it. This rung of the ladder is going to have 480 applied to it. So if I just look at this rung of the ladder, these are now connected in series, R1 and R2. In a series circuit, my voltage is additive. Because these are equally rated, I'm going to take my voltage, 480 divided by the number of resistors. They have to be equally dispersed because they're equally rated. 480 divided by 2 loads, 1, 2, is going to give me 240. Therefore, each one of these loads is going to have 240 volts applied to it. So I can successfully go in here and say this. Right? Again, the reason we can do that, I know that I'm going to have 480 applied here across this rung. The reason I know that is because there's a direct connection back to voltage source, right? I can say the same with this rung right here, 480. So if I just look at this rung, I have 480 volts. If we remember where loads are equally rated, I think I told you this part before, I can, in a series circuit, I can take the total voltage divided by the number of loads. That gives me my voltage to each load. So again, 480 divided by 2 is 240. 240 plus 240 gives me 480. So this rung has 480. This rung has 480. Right? So we've kind of cheated a little bit, but that's okay. We're using what we've already learned and using some good common sense. So at this point, I'm going to drop back. We're still going to have to find the fixed resistance of these things using wattage and voltage. But let's actually, I'm going to delete these for now. And we'll come, remember they were 240. Well, I'll come back and show you why that's going to be so helpful here in a minute. So let's go ahead and find fixed resistance. We know wattage 2000, we know voltage 250. So I'm looking for R. E squared divided by P is going to give me R, right? So I'm going to go E squared, which is 250. Right, so there's my E squared. Forgive me, I don't know how to type in squared on this thing, but divided by, so I have E squared up here, which is 62,500, divided by P, which is 2,000. Just using Ohm's law, that's all. So my resistance of each one of these things is going to be 31.25. Remember, they're equally rated, so I only have to do that once. Okay, so had we not done this little trick to fill in our voltages, the only thing I have left to do is come back and use this R formula. Right? I could come down here and use that using these values to find this. That's fine, but as I said, I really don't want to have to do that. So instead, we're going to go back to that trick we just talked about where we do this, put our 240 back in. What that allows us then to do is I can now use Ohm's law to find these other two values, right? So if I'm looking for I, if I have E and R, I'm going to say E divided by R equals I, right? So I'm going to go 240 divided by 31.25 equals I, which is 7.68. Again, because they are equally rated, I only have to do that once. And then let's find our P value, which I'm going to use E times I. It doesn't matter which one we use at this point. I happen to like E times I. So our P value is 1843.2 watts. So each one of these is going to have 18.43 watts applied. Whoops. And we can do a little checking. This thing was supposed to be 2,000 watts if we apply 250 volts, but we're only applying 240 volts. So what do you know? It's dropped a little bit. Makes good sense, right? So now what we can do is this gets a little trickier. We'd really have to do a lot of lateral thinking to come up with these values. However, and let's run through one here. We've got a little bit of time so the video runs out. Let's say I wanted to figure out my I value here. I can't really use any of these rules still because we still don't have a purely series or parallel circuit. But what I could do, could I determine my I value for just this rung of the circuit? And I can do that pretty easily. So if I just look at R1 and R2, they're connected in series with one another. So I was going to say luckily, but it's not luck, it's science. Their amperages are the same, right? The R1 amperage is 7.68, so is R2. Well, they have to be, because what do we know about, if we're looking at this as a series circuit, what do we know about amperage in a series circuit? It's equal throughout the circuit. Therefore, these better be equal. They have to be equal. They will be equal, right? So the amperage of this rung is 7.68. The amperage of this rung is 7.68. So now let's look at this rung compared to this rung. They're connected in parallel. What's our amperage rule for parallel? Well, it's additive. So could I take the amperage of this rung plus the amperage of this rung to give me total? Well, sure, that's exactly what I'm going to have to do. So I'm going to take the amperage of sort of rung R12, which is 7.68. I'm going to add that to the amperage of rung R34, which is 7.68. I get 15.36. So my total amperage now is 15.36. So now what I've done is I've got two values here. Now I could use Ohm's law to find these other two. I could still use the R. Well, no, I can't use the R formula. I forget I said that. But let's kind of look at this from another way. So we did all this. This was pretty complicated. But let's forget we did that. Let's instead do the same thing for the P values, right? So let's find the total wattage for just this rung. Okay, well, in a series circuit, it's additive. So I can add up the wattage of R1 and R2 to give me the wattage of this whole rung. Then I can do the same for R3 and R4. So then I got the whole wattage of this, the whole wattage of that. How do I find wattage of a parallel circuit now? Well, that's additive as well. So a little typo here, sorry. So if you look at that mathematically, what all that comes to is basically telling you I can calculate this by simply adding all these up, no matter what the combination is. Since wattage is always additive, I can find this by just adding up this whole bottom column, right? Doesn't matter how it's all configured. And this is the part I just sort of figured out now. So this took a lot of logic and thinking to figure out how to add what to what. This, I'm telling you, is basically add up that bottom row. And we'll be there. We'll be good, right? So I'm going to say 1843. I'm going to make that multiplication just to save some typing here. So look at that. My total wattage is 7372.8. Now what I can do, either way it would have worked the same result. But now I can just use Ohm's law to find these other two values, right? So I can say I'm looking for I have E and P. I can say P divided by E equals I. So I can now say P, which is 7372.8, divided by E, which is 480, gives me 15.36. And if you remember, what did we calculate this amperage to be when we sort of did it the long way? What do you know? Exactly the same, right? No difference. And then lastly, I can find R. I can use basically any formula I want to use. I'm going to say E divided by I. Sounds pretty simple. Let's avoid those squares if we can. So I'm going to say 480 divided by 15.36. 31.25. Now that is another interesting bit, and I'm not conclusive enough to say. I think on these square circuits, your total resistance is always going to be equal to the resistance of any one. So again, I'm not quite convinced enough to tell you that for certain, but I think that's going to be true where you have these square circuits, square combination circuits with equally rated loads. I think your total resistance is always going to be the individual resistance as well. And that's kind of a very much longer discussion as to why that is, but keep an eye out for that as well. So there you go, combination circuits. There's not a ton of them. There's 2 or 3 different scenarios, maybe 5 or 6 questions in total, but be on the lookout for those things.